Okay, good evening everybody. In today's class, now we are going to see about timing signals. Okay, so in the last class we saw how an instruction is fetched from the memory, and then you have and then it is brought into the instruction fetch register. So that's how the first thing, and how an instruction is executed. The first and foremost step is to get the data from the memory to the instruction fetch register, right? And then you have an from the instruction fetch register, the data is again moved to the instruction execute register, and through the instruction decoder, that instruction is decoded, and after the decoding, the signal is given to the execution unit to execute the instruction. Like when one set of instruction is being executed by the execution unit, you have the program counter is generally updated, so that while the execution unit towards the end of the one particular execution cycle, the new address, okay, will be placed in the program counter. The program counter address will be updated, and the next instruction will be fetched. So you will find two things are happening here simultaneously. While one instruction is being executed out here, the next instruction is being decoded in the upper part. So you have two distinct things out here: an execution unit and a control unit. The function of the control unit is to fetch the instructions, okay, from the IRF register, decode it, and give the appropriate signals to the execution unit. So while the execution unit is doing certain task, okay, a set of tasks, parallelly the control unit prepares itself to give the next set of control signals to the execution unit. So this in a way, this part, the control unit, moves one cycle ahead. Okay, so trying to keep the instruction sets ready, so that the overall speed of the microprocessor is fast. So that is what instruction set we saw the last time. Now if I take one specific example, just to try to understand what are the timing issues. Okay, so these are the, for a simple add instruction, where the contents of an base register, okay, is to be added with some displacement which is given in the instruction, and then the contents of B2 plus D2, the displacement which you have given, they together are going to form an address location, okay, of the memory. So you take the contents of B2, add with D2, and then you create an address, and from that address you are going to fetch the data and add to the contents of R1, and finally the addition of that contents of R1 and the contents and the data which has been fetched from that particular memory location, the result will be again stored to R1. So this is what the instruction looks like. Okay, so what are the steps? If you try to now write those steps in a sequential manner, okay, trying to understand how the timing signal should flow, then we can write down these steps. Okay, if you see here, fetch the instruction half word, okay, find the add control word sequence. So from the instruction you will have to find out the like it is an register to like memory addition, right? So that particular control word needs to be decoded from the instruction set through the control store. So that particular, so this says find the add control word. Okay, so that is nothing but decoding the instruction. Okay, once that is happening, okay, fetch the remaining half instruction word. Okay, why is that so? Because here only we have got the half instruction word. In the rest of the half instruction word, we have that data which requires to be added, right? So in certain instructions, and it might stop here, there could be only one word, but in certain instructions, like in this particular example which we have taken, we need to have this D2 data also in the instruction. So you need to get the remaining half instruction also, right? Okay, wherein we are going to add this data to the contents of B2. So you have that instruction. Then calculate the operand address. Okay, now you add D2 with B2 and compute the new address from where the data needs to be brought, and then you now put that address into the computed address into the AO register, and from the data register you get the data, and then now you add the data which has been fetched from the memory with the contents of R1 register and store the answer into the register. So these are the things which we need to do to execute this instruction. So these are the various steps that are involved, right? Now if you see here, before just going to the next block, let's try and recollect what are the things which are there in the execution unit. So you have certain registers out here, you have a program counter, you have an address out bus bar. So whenever a data needs to be fetched from an external memory, from the memory, that address is placed in the AO, okay. And then you have a data bus, and whenever you have to fetch a data, the memory places, the address is placed here and the data is placed here, and then the data comes into the DI. Similarly, when you have to write a data into the memory, again you place the address here, and you place the data to be written into the DO bus. So this is data out register, this is the data in register, right? So these are the, and then you have two internal bus. So in ALU, if you see here, this is generally one of the inputs will be from the A, and the second input will be either from the internal bus or from K, and K can take a value of 0, 1 and -1. So these are the things which we did in the previous class, okay. Similarly, once when we are fetching the new instruction, okay, when we are fetching the data, it comes into the DI register, and similarly when we are writing data, it goes to the DO register. But whenever we are fetching an instruction, okay, which needs to be executed from the program counter, whenever the data is placed from the program counter, when it is placed to AO, then the next instruction will be brought into the IRF, okay, instruction fetch register, and then from IRF in the next cycle it goes into the instruction execute register, okay. So these are the things which are there inside the ALU. Okay, now let's split that actions of add, okay, taking into consideration the various timing aspects, okay. So first what we are doing out here is we are reading an instruction, right, and then now see D2 and B2, okay. So this comes from the IRE register, right, from in the IRE register, because when we discussed in the last state, some instructions, okay, the data will be there like this displacement, okay, this displacement is available in the IRE register itself. So in the here the control word which comes from the control store just tells the execution unit to add the contents of the of a particular register. It just tells add contents of a register with a displacement, okay, only that much. Which register, okay, that comes from the IRE, and what data requires to be added, that also comes from the IRE, okay. So when we saw this in the last class, I have explained that, okay. So control word just tells it is just a register and displacement addition, okay, it just tells that much. Which register and what is the data to be added, that comes from the IRE directly out here, okay. So that is one shown here. So once this comes from the IRE, and the contents of the base register is added to D2, so in the ALU, okay. Once this action is done, so the new address is registered, okay, is computed. So that calculated new address is going to be placed in the address out and register, and you have and then you have the data from that memory placed onto the DI register, right. So this is how this is going to come. The data is going to be placed into the DI register, okay. Now the next step would be, now you have the contents from that memory, okay, which has been computed in the earlier state. That data is available, contents of R1 is available, the ALU is going to add these two, right. And then once it is added these two data, it is going to be placed into R1. Now until now we were speaking of a program counter incremental by 1, okay, every time. Here we are talking about 2. assuming that the instruction set is often a word instead of a byte. Okay, so that is the reason we are writing +2 here instead of +1. So for every instruction it has to it will be not a byte, but it will be a word here. So you have to keep adding +2, so that it keeps incrementing by 2 here. So every instruction is of 2 byte. Okay, now so that is the change from the previous lecture here. And now the new updated value of the PC is going to be put into the ALU. Okay, from the ALU the data is being pushed to PC. So the PC contents gets incremented by 2, and then you place that in the IO buffer, and you get it into the instruction register. Okay, so this is about this. Here we are speaking about without an overlap case. Okay, in case we can also do some overlapping, like from level 1 to level 2. When we moved, we saw that some instructions can be executed parallelly. So that is what is done out here. So you see, from in the ALU you are adding D2 to B2. Okay, whereas parallelly you are reading the next instruction out here. So two parallel operations also can happen out here, and similarly read operand half word. So the value now here from the new address which has been generated here by adding these two. Okay, that you are placing into the address bus bar, and the new data from that memory location is being placed into the DI register. Okay, then you increase the count of the PC by 2. Again, why instead of 1 plus 2? Because now we are talking about instructions which is of 1 word length, so it is increasing by 2 instead of a single byte instruction. It is here 2. So that is the reason you are adding it +2 out here. Then you put the data, new data, into the PC, into the ALU. Okay, then you add the data now here, right? The data which is there in the new DI and RI, you are adding it, and then you are updating the contents of R1 through ALU. So you will find here from 9 here, when we are doing some overlap out here, so we will end up having only 6 instructions. Okay, so this is this is exactly similar to what we did from level 1 to level 2, right, when we moved. Now if I just again expand, try to analyze what actually timing wise how the data is getting transferred from register to register. So I have written this level 2 flow chart once again, and try to analyze what is happening. Okay, now if you see PC, initially what I am putting PC to ALU and AO. Okay, and then from this PC count has been already been computed in the previous cycle. So the next instruction is being fetched out here, right, by placing that address into the AO, right, and parallelly the first line, what is it doing? It is putting the contents of PC to AO. So the IRF register, okay, is getting updated with the next instruction. Okay, that is the first part. In the second part, what is happening? Again, PC is being brought to ALU, and you are adding +2. Again, we are talking about here +2 because we are telling each time now the instruction is bigger, so each time and it has to be added 2 out here. So you have an ALU. Okay, now we are assuming now if you see the timing diagram out here, right, so T1 is a register, right. So once you place the data in a particular clock cycle to the ALU, and T1 can be updated only in the next clock cycle, right. So that is why this T1 initially it was we assumed that when we made the flow charts, and we didn't think too much about the timing aspect, and that's why we never bothered about. We assumed that the moment this operation is completed, data is available in T1. Okay, now we are taking into consideration that T1 also T1 is a register, and it requires a clock, positive edge of the clock. So during the first clock, okay, these actions are happening. In the second clock, okay, and from the contents of the ALU, it is coming to T1 out here. right? And then this is what we thought. Once we transfer the data from ALU to T1, we are going to put new data B2 and DI into the ALU for an addition. Okay, so but here if you see here, there is an issue, small issue out here, right? So here from ALU we are going to get the data to T1. At the same time, we are telling we are going to put these two data. We are through B2 is also being put to ALU, and contents of DI is also being sent to ALU for addition now here. So whereas what we are supposed to transfer to T1 is the result of the previous operation. So here if you see here, something is being returned into the ALU, is being tasked with a new addition sequence here, whereas the result from the previous operation is being pushed into T1 also, right? So now you will find there is an issue out here. So we will see how this issue is resolved by using multiple phase clock. Okay, so there is an issue out here. So time being we'll leave that issue like that, and we'll revisit this issue. Okay, then you have from ALU to coming to AO, and from the external data bus it is coming to DI, and T1 is coming to PC. So the PC has been incremented now out here, right? So from the data in external data bus also it's coming to DI, and from the ALU to the AO. Okay, so this is the what we discussed just in the earlier slides. Okay, here we are adding these two datas. Okay, what we are actually doing is we are doing this instruction like I explained in the beginning. So this is the instruction. So that is what is being happening here, and this is again storing the data finally. Here also if you see in the timing diagram, there is an issue out here also. So this is the normal timing diagram which we have done earlier also. Here also we assume that data is coming from IRF to IRE. Okay, at the same time we are telling that the new data is coming to IRF, right? So how can a register read and how can we read a data from a register and write a data into the register in the same clock cycle? So these kind of issues were not earlier discussed in our earlier classes. We assume that lot of things are happening like this, but if you get into the nitty-gritties and try to analyze the timings, you will find here data is being written into T1 from ALU, and new data is being data is from the ALU, some data is being read into T1 from read here, and data is being written to T1, new data is being written into ALU. So there is a clash out here. So these kind of issues were not discussed earlier, and today we are going to see. So if you the solution is not to use different clock cycles, right? That will take that much more long time, that much more clock cycles if you try to segregate these. So a better option is available, which is known as multi-phase clock. Okay, so now what is a multi-phase clocks? So how to generate first of all a multi-phase clocks? Okay, so if you see this is just a simple flip-flops which are put in series out here. You have a shift right operation. So initially suppose I give 0 0 0 1 out here, or let us say 1 0 0 0 0 is the initial value. So with every clock pulse, okay, so from the last it is again brought back as an input out here. Okay, so this T0 doesn't mean it's a toggle flip-flop. They are all D flip-flops, and T indicates just because it is a timing signal, so that is why it is written T0, T1, T2, T3. Okay, it doesn't indicate a T flip-flop, it indicates an D flip-flop actually. Okay, so the data is being shifted from left towards right. Okay, so you have a 1 0 0 0, and in the next clock cycle it will be 0 here, this will go 1 here. Next clock cycle that 1 again will get shifted to T2, and finally it will go to T3, right? So if I see the waveforms out here, so this is the clock signal. So initially T0 will be 1, then T1 will be 1, then T2 will be 1, then T3 will be 1, again T1 will go 1. So this is, so if you for the same clock cycle, now I have generated 4 out of phase signals. Okay, so they are all 90-degree out of phase, you could call. So they are T0, T1, T2 and T3. So these are known as multi-phase signals. Okay, so these kind of signals will enable us to use the same clock frequency but do multiple actions out here. Okay, so how that is done, we will see that. So essentially first we require these kind of clock signals. So let's see one or two more schemes where we can generate these kind of clock signals, and then we will try and understand how these clock signals can be used to overcome the problems which we had foreseen earlier, right? So you could all, like in this case what is happening is we required an 4 flip-flops, right? So so similarly for an 8-bit you will require an 8-phase, you will require 8 counters, 8 flip-flops. So to reduce the number of flip-flops, you can just use an counter and a decoder also. Like here, if you for example, if you use an 2-bit counter, a 2-bit counter can be realized by 2 toggle flip-flops. Here it is toggle flip-flops. Okay, T. So it is given 1 means it is going to toggle every time. Here also 1. This is not timing signals. T0, T1 means T flip-flops. Okay, so these are the 2 flip-flops out here. So you give a clock here, and the clock has to be negative edge triggered. Okay, to get an increasing sequence, right? If it is a positive edge triggered, then it will be a down counter, and if it is a negative edge triggered, then it will be an up counter. Suppose 0, initial count is 0 0, then it is toggle. So in the next clock this will go high because it is given out here. Okay, but this is making a transition from 0 to 1. This will not change. Okay, because it is negative edge triggered. Next clock again this will become 1 to 0, and that is the time this will become again this will toggle from 0 to 1. So you have 0 0 1 0 and then 0 1, and then again in the next it will become 1 1, and then again it is going from 1 to 0. This will also go to 0. So whenever this is making a transition from 1 to 0, this will also make a transition. It will toggle essentially. Okay, so this way you can use a 2-bit counter here, and then you use a decoder. So decoder, what does a decoder do? For 0 0 this line will go high, 0 1 T1 will go high, okay, 1 0 T2 will go high, and for 1 1 T3 will go. So if you see in this particular configuration, I just used 2 flip-flops and 1 decoder, and I get the required timing signals. So this requires lesser the same from as compared to this circuit. Okay, because flip-flops require a large number of transistors, right? So as compared, here only 2 flip-flops are required as compared to the 4 flip-flops out here. So that is the advantage of using a counter and a decoder, right? Or you also have something known as a Johnson counter out here. Now if you see here, 4 flip-flops have been used out here, and they are all like from Q to D, Q to D, Q to D, and here Q bar is fed here, right? So initially I have all 0 0 0 here, and then in the next clock cycle 1 will be fed from the left. They are all shift right, so 1 will get in here, again 1 in the next stage, again 1 will come here. So this is the truth table. Okay, so this is how it will go: 0 0 0 1 0 0 1 1 0 0. So this is the kind of pattern which you will get. Now after 8 it will go back to again 1. So 8 different patterns you will get here. So from those 8 different patterns you can use these kind of gates to get the clock signal. So if you see when it is all zeros out here, so S0 it is coming from the bar signal out here, Q bar, from Q bar here, right? The next is also a bar. So when it is all 0 zeros, this one will be high. For the next one it is 1 out here, right? So if it is 1 out here, means it is coming 1 here, so this will go 0 out here, so this will get disabled. Whereas this is coming from here, so now S1 will get enabled. So each as this count keeps moving from 0 to 8 to come to 0, one of these signals in a sequential manner, one of them will go high. So by using 4 flip-flops I can get an 8-phase signal out here. Okay, so this is also used. This is known as a Johnson counter. So this is also used to generate the signals. Okay, now coming back to our main block diagram. From the previous block diagram, only a new thing which has been introduced out here is something known as instruction register for decode. So one more register has been included out here. Okay, that is because like once an instruction register and instruction decode is happening, okay, the instruction will be going from IR decoders through the control state and through the control word out here, right? It will take certain clock cycles, right? But till that time, some part of the instruction fetch needs to be preserved out here, because here we saw like in the earlier case also, some data like here in this, where was that example, this data, okay, that comes from the IRE. So right, so by the time this signal gets decoded, I have to keep I can't change this data with I can't update this with the new instruction, because this control word decoder finally, which is being given to the execution unit, requires this some part of the signal coming from the control store and some part coming from the IRE. So what I am doing is I am put one more register in between out here. I am going to clock these with different clock signals. Okay. So time being, just we'll leave it at here, and we'll see these clock signals slowly, okay, in the next few slides. So here I am giving instruction register for decode. Okay, one additional instruction register is available out here. Right now, let's see how the timing signals are organized. Okay, during the phase 1, the source register is gated to the internal bus. Okay. So one register, once you have transferring a data from one register to other, okay, from one source register to other, okay, the other register could be AO bus register or the data in register or the data out register, whatever. So the source register, okay, during phase 1, source register is gated to the internal bus. Okay, during phase 2, the signal on the internal bus is amplified. Okay, and in the phase 3, the signal on the internal bus is gated to the destination. Okay, and in the fourth phase, the bus is returned to a neutral value. So we have to remember how these phases work, then everything will be clear. Okay, so in the phase 1, the source, if I go back to the block diagram out here, right, if suppose I have to transfer some data from PC to ALU, in the phase 1, PC will be connected to the internal bus. Okay, in the phase 2, the data will be stabilized in the internal bus, and in the phase 3, the ALU will be connected to the data bus. Okay, so we have seen like in the hardware implementation, right, there will be some switches which will connect PC to the data bus, then data bus to ALU. So they are all different switches, right? So they will be controlled by different phase signals here, right? It is not that a PC and ALU will be connected at one go. Okay, in the phase 1, PC will be connected to the internal bus. Phase 2, you don't do anything, you will allow the data to stabilize in the internal bus A, and the ALU will be triggered in the switch which is going to connect this data to the ALU. That will be powered only in the phase 3. That is the same for other, whenever a DI data from DI requires to be brought to ALU, or from the ALU to T1. Okay, in all those cases, it will be a 3-phase signal will be, clocking signal will be required. So with these 4-phase clock, we will see the problems and how they are eliminated. Okay, so before that, let's have a look at this block diagram also, which we have already done. For the ALU, one data comes from the A bus. Okay, the second data comes either from the B bus or K. Okay, now the K can take 0, 1 or -1. So that particular so you have a multiplexer in between, which will select either B bus coming to ALU or 0 or 1 or -1. Okay, this we saw in the hardware implementation class then. And similarly, not all whatever the ALU is doing, not every time the data is stored into a T1, but you have to select, okay, you have to select which outputs needs to be loaded to T1. Okay, not all additions and subtractions and on operations of ALU will be routed to T1. Okay, so whenever, only for certain cases, the output of ALU will be routed to T1, and that will be done through load on a T1. Okay, so a phase signal, one of the phase signals has to come to load T1. Similarly, flag registers. Okay, so you have once the ALU does an operation, okay, depending on whether you need the flags to be operated. Like, so for most of the address computing instructions, we don't need to update the flags, right? So whenever the PC is incremented, right, or you are computing a new address, the flags need not be updated in those cases, and hence you have another load CCR signal also. So just remember, these are all vital things which will allow us to resolve all those problems which we discussed earlier. Similarly, ALU can be told, generally you give a select signal and you have an add signal, because that is the most used operation. So you have the add signal here, but you can also give other instructions, okay, through the IRE. Okay, so this is also available through the MUX. So this we saw in the last. Now if you see here, now the same chart which we discussed earlier, now we will see why there is no problem in writing like this. Okay, so that justification will be given out here. I will explain that, because we have now multiple phase signals. Okay, now if you see here, for the first block out here, you have PC contents will be placed to the A bus during clock phase 1, and it will be returned to ALU in the clock phase 3. Okay, so similarly, now there is one issue which you need to remember here. Since the address bus, okay, also from the data from the PC, the data will be placed into the address bus in the phase 3, right? So memory has to operate in a fast. Okay, so unless the memory operates in a fast, because there are only 4 clock cycles, so the address bus will be updated only in the 3rd clock cycle. So immediately once the address is placed, the data should be available in the EDB, like external data bus, so that the IRF can be now powered with the phase 4. Okay, phase 4, so that or the next clock cycle, clock 1. Right, so you will have to, so this memory from data when we are retrieving from the memory has to be fast, otherwise you will have to insert some some timings, okay, some gap into the timings. Okay, so that is the reason generally we have an RAM or a cache, right, cache memory. So we will discuss about the cache memory also in the next class. Okay, so that is one. So you don't find any issues here. There was an issue out here. Okay, so we will see in the last. So now if you see here, from the ALU to T1, okay, we can trigger this signal in phase 1, so that the whatever was the value in the ALU, okay, will be saved into T1 in the first phase of the clock itself here, right? And then at same time, from B2 and D1, and data is being placed to ALU. So this will take 3 clock cycles, right? In the phase 3 only this data will come into ALU, right? So now if you see here, there is no clash out here, right? In the very first clock, if I go back here, in the very first clock, the data of the ALU will be transferred to T1. So I am going to trigger these two with phase 1, okay, with phase 1. And whereas the data which I am placing here, okay, from the PC, okay, that will take 3 clock cycles to reach ALU. And now if you see here, since we are using a multi-clock, hence in this single block you can write, you are reading the data from ALU also, and you are giving some new data into the ALU for the new computation. So all these things have been placed in a single block. And why it has been made possible? By using multiple clock. Okay, So in the phase 1 clock, this data is being read from ALU into the T1, and this data will come into the ALU after 3 phases. Okay, so that is the reason you will find here. Okay, so there is no problem, okay, having read and write operation simultaneously into the ALU into a single block, because although this is a single block, we have multiple phase clocks coming here. Okay, now similarly in A3, okay, here if you see here in the A3, from the ALU it is being put to AO. Why? Because like we initially discussed, our what was the main aim? To add the contents displacement with the contents of B2 and get the contents that from the memory. So from ALU you are directly placing it to AO, and in this case if you see here, T1 is not being updated, right? So that is the modification which we are not going to update T1 with every ALU operation. So in this case also, if you see here, we are adding, if you see, go back to our initial where we started, what we wanted to do was find out this memory location, contents of B2 we are adding with T2, finding out that particular address and getting the data from that address and adding it to R2, right? That is what we started our class today. So if you see here, here we are creating the new address, and then that address, instead of getting into T1, we are directly placing it to AO, and T1 was holding in the previous cycle. The incremented value of PC was given to T1, and now from T1 I am giving it to PC. Now if you see here again, there is no clash out here also. Why? Now if you see here, not all instructions of A2 is being brought into T1, because you have you have placed one more switch in between out here, right? So that is why there is no issue with this particular block also, right? And here, so as such, in here it was a simple case where there was no issues. A D1 register is brought into ALU. No, the contents of DI. Okay, what is the content of DI? Once we added the displacement with B2, from that memory location some data was brought in that was available in DI, that is being brought into ALU. Contents of R1 is brought into ALU. So this will again take 4 clock cycles for this computation. So there is no issue. So it will take first the data will be placed, in the third cycle the data will come to the ALU, and in the end of the fourth cycle only the data will be available here. So all the 4 phases will be used here. Now in the final one, again you will see from the ALU it is going to the contents is being updated with R1 out here. Like from the instruction fetch, the data is being brought to instruction execution, and also if you see here, the new data is being put into IRF. Okay, so here this also will be given different phase signals. The IRF and the IRE will be triggered with different phase signals, so as to avoid a clash out here. Okay, so that we will see the next. So if you see here, now if you see in this particular block diagram, see when an instruction is brought out here, okay, so it is then brought to IRD, and then this is going to take 1 microcycle. Now what is 1 microcycle? It consists of 4 cycles. If I go back here, these 4 cycles together is known as 1 microcycle. Okay, these 4 signals together. Okay, so now here this is going to take 1 full microcycle out here, right? So 1 microcycle is required out here, right? And then this requires another half microcycle. This requires another half microcycle, right? So by the time this signal comes from here to here, okay, 2 microcycles are required here. So the instruction fetch has to get at least 2 cycles. It has to move 2 cycles ahead, right? Because once the execution unit completes the data, okay, for this instruction to complete it, it will require 2 microcycles, right? So this has to be ahead of the execution unit. That PC value of corresponding to 2 microcycles should be placed here to give it adequate time for it to get decoded out here. So accordingly you will find that instruction fetch has to be incremented and placed in advance. Okay, the PC count requires to be placed here in advance out here. Okay, so that is. Now if you see here, the PC, this is triggered by phase 1, this is triggered by phase 4. Okay, why it is triggered by phase 4 is in each execution unit towards the end of the end of an each execution unit, a new program counter will be updated, right? So that is what we learnt in the hardware flowcharts, right? Towards the end of any execution cycle, the last thing would be to update the PC with the data that is required for the next cycle, right? So that is why it is being triggered with phase 4. Okay, so that will come here, right? And now if you see here, since this data requires to be it has to travel from here to here to come here, whereas some part of the instruction fetch needs to be preserved here, because finally the data which comes here needs this information also, so that the execution unit is like this would say, suppose register to register 1, contents of register 1 needs to be added to register 10, right? So what is going to come from here to here, that is register to register addition. And where is the information which tells, okay, which is register 1 and register 10 is to be added, that comes directly from here. So that information, these two will be mixed together, right? That we saw in the hardware implementation class, right? So now that is the reason this is been triggered by phase 3 signals, so that this by the time this signal this is triggered, whereas this is triggered by phase 1 signal, right? So by the time the signal comes here, this will be preserved, because this is on, this will the next data will be updated only in phase 3. So excuse me, so that is the reason this is being triggered by phase 1 and this is being triggered by phase 3, right? So this is how we can using multiple phase clocks, okay, we can ensure that these signals are working at a faster rate. Okay, not if you don't use multiple phase clock, you might require, instead of 1 clock cycle, you might require 4 clock cycles for the entire thing to complete. Okay, so using multiple clock, okay, of different phase clock signals like these, okay, ensures a staggered operation of the clock signal. Yeah, using like these multiple signals ensures that the perfect timing, it gives time for each unit to complete its operation. Okay, so that is the reason we use multiple clocks in these. Okay, now within the control word, now we are talking about the control word, this control store, right? Control store is nothing but like a ROM, right? Reading, you place an address. Okay, the address is placed, and like if I go back here, the address is placed here, and the code is given here, the data is given here, which is the control word, right? From the control store you get the control word. So that particular this is nothing but in hardware wise it is just like a ROM. So here also, instead of having a single big ROM, we can this is how it is organized for a fast operation. You have an address decoder here, so it is distributed as an m rows of 16 words, okay, 18 bits per word, and n rows of 4 words. Okay, so if you find here, once an address is placed, you will either select one of the m rows or one of the n rows from here. Okay, so but if you see here, 16 words are there, out of that only 1 word is required, right? So you use one more 16 into 1 mux. Okay, at this mux also, this will be part of the address only. So so you can use this 16 into 1 mux. Similarly, here also one of the n rows is selected. I will have 4 words being selected. From the 4 words I can select 1 word. So I have using an 4 into 1 mux. Okay, so the reason of having like this is, so in the last class we are going to read about a memory organization. So if you organize the memory in this manner, you can use decoders. Decoders are all what? Generally it is AND gate. So you can use an AND gates with a small fan in, that is the number of inputs. So right now let's restrict that by using these kind of configurations. The decoder becomes faster and power efficient, okay, and simple in design, okay. Why that happens, that we will look into details in the memory organization class, okay. So this is one, okay. This is again same thing, which okay. And now towards the end, let me take some time and explain you this. What is happening is here, if you see here, exemptions is whenever there is an there isn't a valid instruction, it is known as exceptions, okay. So there could be some or interrupts, you can call it interrupts also. So it could be an internal interrupt or it could be an external interrupt. Like a program is running, but somewhere there will be some interruptions. So the interruptions can be internal or it could be external, okay. Internal again could be immediate, okay. That means immediately you have to service that in interrupt request, or it could be deferred. That means you are presently doing some running some code, you finish that, complete that particular instruction, and once you complete that instruction, then you can service this interrupt request, okay. That is known as deferred. Similarly for external also, you can have an immediate, okay, and you could have an deferred, okay. So we'll take some examples and then it will be clear, okay. Now if you see here, internal interrupts, what are, okay, so that comes within the chip, okay. Suppose you have a divide by 0 coming in the instruction, you are doing some calculations and you have reached an state where it is divided by 0, okay. So in that case, what you will have to interrupt the program, and then you go into a subroutine, which you might have done it in your microprocessors class, right. So you go to a subroutine and you pop up an error message, right. So these are all the kind of interrupts. Similarly, when you are doing an addition or something or a multiplication, if you are encountering an overflow condition, right. So that is again a kind of an internal interrupt. Or you could have an trace. Trace is nothing but when you are debugging, so you would want the program to stop at every stage, so that the result of each stage is stored into a register for a person to analyze what is the problem, okay. So these are all the internal interrupts, okay. There could be external interrupts also. There could be a bus error, okay. What is bus error? Because you are trying to read and write information, but then the bus is not able to catch up with your the data bus is not able to catch up with your speed, okay. Those kind of errors can, so they are all that has to be attended immediately. So these are all example of an immediate interrupt signal, external immediate, okay. There could be a peripheral chip request, that could be like a request from an printer or from a keyboard and all. So they may not be that very important. You might want to finish off what instruction you are doing and then attend to that request, okay. Reset request, right. Again reset request also may not be that important. Once you are pressing the reset button, not that whatever is the program being run that will be in stopped, it will try and finish off that program and then only attend to the reset. So these could be some of the deferred external inputs, okay. Bus error, you could say it could be an immediate type and external input. Similarly, there could be some temperature overshoot, such kind of things from the PCB, such interrupts coming, okay. So these are the various kind of interrupts which are there. Now how to incorporate those things in our module. So if you see here, initially here, if I go this block, this was the block which we learned earlier, right. So within these blocks, now some extra blocks have been added out here, right, so if you see here, this is going to the control store. So whenever there is an immediate external interrupt, okay, so you give an immediate external input trigger, you are including an one more multiplexer out here, right, and here we are giving immediate external input signal. So once you give this here, the new address where that subroutine for that immediate and external interrupt is given. So that address will be fed into the control store. So the program will now go and try to run that program. So the PC will be accordingly updated now with the address of the interrupt subroutine, right? So that signal comes from here. So you have a immediate interrupt bit out here. This is a new multiplexer block which we have introduced to service this immediate external input address. Okay. Similarly, you could have an internal also. So for that, you can have the immediate address field coming from the internal side only. Similarly, you could have deferred external. Okay, so in the deferred external, so you have this multiplexer after the control store address multiplexer, because it will allow this to complete the present instruction. Okay, so because it is deferred, it is not that very important. So these deferred signals are placed at a second level here. It is not placed immediately close to the control store. This multiplexer is directly controlling the control store, whereas this multiplexer is placed in one. It will allow this to complete the present instruction, and only then it is going to service these interrupt requests. Okay, so these interrupt requests have been placed towards the right of the control store address multiplexer. Okay, so you have external interrupt as well as the internal interrupt out here, right? So this is all about interrupts and timings. So we'll call it off for today here.